All right, guys, this is our third and final lesson for this week, and we're going to be covering rational functions and their graph. All right, so again, let's go ahead and dive into this, and let's get this all wrapped up for this week. Okay, so some essential understanding we will need to know for this. If a function has a polynomial in its denominator, its graph has a gap at each zero of the polynomial. The gap could be a one-point hole in the graph, or it could be the location of a vertical asymptote for the graph. A rational function is a function that you can write in the form of f of x equals p of x over q of x, where p of x and q of x are polynomial functions. The domain of f of x is always all real numbers except for those in which the q of x can equal 0. Again, remember, in our fractions, we do not want 0 in our denominator. All right. Here are the graphs of three rational functions. Again, we're going to see all types of these graphs today here, guys. Again, you could see holes in them as we see there in that second example right there. We could see asymptotes as we see right there. And we're going to dive into this in good detail here so that you understand when you'll see these graphs. Okay. So let's take a look here. We do have a key concept and some that you need to know. Again, a lot of vocabulary here. For the first rational function, y equals x squared over x squared plus 1. There is no value of x that makes the denominator 0. The graph is a continuous graph because it has no jumps, breaks, or holes. You can draw the graph and your pencil never leaves the paper. For the second rational function, y equals x plus 3, x plus 2 over x plus 2, x cannot be negative 2. For y equals x plus 4 over x minus 2, x cannot be 2. The second and third graphs are discontinuous graphs. So there's your difference in the continuous graph and discontinuous graphs. So let's go back and look at those over here. So as we can tell here, this first one right here, as we can tell, is a continuous graph. There is no point at which we ever come to a stop or there's an asymptote there. In our second graph here, there is only 1 point on our graph where x cannot equal 0, and that is at when x is negative 2. So on our graph right there, there would be an open circle, which makes this graph a discontinuous graph. On this one over here, we have our asymptotes right here on our graph. So again, from those right there, since there are asymptotes, that means there are points that cannot be reached, which makes this a discontinuous graph as well. So again, if you can draw a graph where there is no stopping points whatsoever, it's considered a continuous graph. So that's the difference between continuous and discontinuous. Point of discontinuity. If a is a real number for which the denominator of a rational function f of x is 0, then a is not the domain of f of x. The graph of f of x is not continuous at x equals a, and the function has a point of discontinuity at x equals a. So again, kind of like our domain and range when we say those points cannot be what they are, that's also considered our points of discontinuity. All right. The graph of y equals x plus 3, x plus 2 over x plus 2 has a removable discontinuity at x equals negative 2. The hole in the graph is called a removable discontinuity because you could make the function continuous by redefining it at x equals negative 2. So that f of negative 2 equals 1. Okay. So again, if there is a hole in the graph, then we're going to make that a removable discontinuity. Okay, and then that third graph, the graph of y equals x plus 4 over x minus 2, it has a non-removable discontinuity at x equals 2. There is no way to redefine the function at 2 to make the function continuous. So again, if we have asymptotes, those are going to be non-removable discontinuity. So that's the difference there. Okay. All right, first example here. So again, we're going to have three different problems here for finding points of discontinuity. So our first one here, what are the domain and points of discontinuity of each rational function? Are the points of discontinuity removable or non-removable? And what are the x and y intercepts? So here's our graph, x plus 3 over x squared minus 4x plus 3. Your first step, if you can, you need to factor your equations there. So you need to see if you can factor x squared minus 4x plus 3. In this instance, you can. If you can factor, you have to. So that actually factors down to x minus 3 and x minus 1. Okay, so since from there, that's when it's going to tell us where we cannot have our holes at right there. So again, that always set your denominating equations equal to 0. So I'm going to set x minus 3 equal to 0 and x minus 1 equal to 0. And that's where we get our 2 points of x equals 3 and x equals 1. So that means the domain of the function is the set of all real numbers except for those 2 points of x equals 1 and x equals 3. So again, those are going to be our holes. So if those are the holes, then those are non-removable points of discontinuity. Okay, and those are going to be at x equals 1 and x equals 3. The x-intercept occurs when the numerator equals 0 at x equals negative 3. And to find the y-intercept, you're going to let x equal 0 and simplify. So again, all you do is once you have that, then you go back and plug in 0 to find what the y would be for all your x's there. So again, here was our original equation of x plus 3 over x minus 3, x minus 1, and they just plugged in 0 for all of the x's, which reduces down to 3, negative 3, and negative 1 on the bottom. And then those multiplied would give me 3 over 3, which does equal 1. So that's our y-intercept right there, which is 1. Y equals 1. Okay. Here's another example. Same type of problem, same question. So on this one here, x plus 1 on our denominator. Remember, we cannot use difference of squares if there's addition there. That only works with subtraction. So in this instance here, that cannot be factored, which means since that cannot be factored, there are no values of x that will make the denominator of 0 because all numbers are going to end up being squared. Again, anytime you square something, it's going to make it a positive number. So again, even if I put negative 1 in that x right there, negative 1 times negative 1 is a positive 1, and 1 plus 1 is 2. Okay, so that means that the domain of this function is going to be all real numbers, and that means that there are no discontinuities. Okay, so then that means the x-intercept, which is the top part, where the numerator equals 0, is going to be x equals 5. Okay, remember, that's how you find the x-intercept. You go to the numerator, set it equal to 0, and it should equal 5. To find the y-intercept, go back to your original equation and plug in 0 and simplify. So again, we're left with 0 minus 5 over 0 squared plus 1, which simplifies down to y equals negative 5. Okay, we have one more we can look at here. All right, in our equation for letter C here, x squared minus 3x minus 4 over x minus 4. We just saw this problem beforehand. Again, we can simplify this equation here, which should reduce down to x minus 4 and x plus 1. That can be factored there. Then we're left with x minus 4 on the bottom. Okay, so again, this function is going to be undefined where x minus 4 equals 0. Again, we cannot have 0 in the bottom part of our equation. So that means that the domain of the function is the set of all real numbers where x cannot equal 4. Again, they got 4 because they set x minus 4 in that bottom number right there equal to 0 and solve for x, which is how they got x equals 4. So luckily, since they both have an x minus 4 on top and bottom, those do end up canceling out. That simplifies down to y equals x plus 1. Because again, those x minus 4s on top and bottom cancel out. Now, you still need that x minus 4 for when you're trying to define your domain. Because again, we still have that fraction at the beginning of our equation here. But if I'm looking to simplify it, it simplifies down to x plus 1. Again, where we can't have x equal 4. So that means that there would be a removable discontinuity at x equals 4. So at x equals 4, we'll have y equals x plus 1, which again, 4 plus 1 would then reduce down to 5. So again, that's what our y would be if at x is 4, our y is going to be 5. That's all they did. They just plugged in their x into the simplified equation and solved for y. So you can redefine the function to remove the discontinuity. So again, you have your original equation where x cannot equal 4, and then you have the solution for that when x does equal 4, y has to be 5 then. So again, you'll have two separate equations. Okay. The x-intercept occurs when the numerator equals 0. So that's how you're going to find the x equals 0. So again, in our numerator there, we have our only equation here of x plus 1. So if I set that equal to 0, x should equal negative 1. to find the y-intercept, I'm going to go back to my original equation up here, the x minus 4 and the x plus 1 right there, over x minus 4. So again, that should reduce down to, when simplified, to negative 1. Oh, sorry, positive 1. So again, to find the x-intercept, you're using the numerator. To find the y-intercept, you're plugging in 0 for every single x that there was. Okay? All right. Again, you could have also even used the new equation also. That would have gave you the same answer. So again, just understand that there's more than one way that you can solve these answers. All right, so key concept here. Vertical asymptotes. We're about to cover vertical and horizontal here. So vertical asymptotes of a rational function. The graph of the rational function has vertical asymptotes at each real zero of q of x if p of x and q of x have no common zeros. If p of x and q of x have x minus a to the power of m and x minus a to the power of n as factors, respectively, m has got to be smaller than n. M is less than n. Then f of x also has vertical asymptotes at x equals a. Okay, so let's take a look at that here so that we can get a better understanding of what that looks like. Finding vertical asymptotes here. So what are the vertical asymptotes for the graph of y equals x plus 1 over x minus 2 and x minus 2? So they've already factored it for us. We don't have to do any factoring here, right? So to find those, so since 2 and 3 are the zeros, again, the way we can find that is set your two bottom parts, the two bottom factors equal to 0, solve for x. So I would set x minus 2 equal to 0, x minus 3 equal to 0, solve for those x's. That's how we get 2 and 3 to be our zeros there. X equals 2, x equals 3 as the denominator. And neither is a 0 of the numerator. So again, since both of those, if I can plug both of those into the top and that doesn't give me 0 in there, then the lines of x equals 2 and x equals 3 are your vertical asymptotes. Now, again, that changes if that is in the numerator, but understand, since they are both not in the numerator, then they are both your vertical asymptotes. Okay? All right. So we've covered vertical. Let's take a look at horizontal. So horizontal asymptote. To find the horizontal asymptote of the graph of a rational function, compare the degree of the numerator m to the degree of numerator n. So this is where we got to be careful. Now we're comparing degrees. So what's the highest degree on the numerator and what's the highest degree on the denominator? So if m is less than n, then the graph has a horizontal asymptote at y equals 0 or the x-axis. Okay? So again, that is if the bigger part on the numerator is smaller than the numerator. If the numerator is bigger than the numerator, then the graph has no horizontal asymptote. Now, if they are equal, so these are your three options. M is smaller than m is bigger than n, and if they have the same highest degree, the graph has a horizontal symmetry of y equals a over b. And what they mean by that is a is the coefficient of the term of the greatest degree in the numerator, and b is the coefficient of the term of the greatest degree in the denominator. So again, you're looking at then if the degrees are the same, so if they both have x squared and x squared in there, then you're looking at the numbers in front of those x squared. So like if they was like 2x squared and just x squared, then it would be 2 over 1. So then you would simplify that down to 2. So again, if they are the same, then you look at the numbers in front of those highest degrees. So make sure you're careful about that. Okay? So we do have some examples of these so that we can get a look at this. All right. What is the horizontal asymptote for the rational function here? So again, you're looking at the degree here. So again, the highest degree on the top, again, not the coefficient, the degree. If I do not see a degree there, then again, I can always assume that that degree is a 1. So then the top right here, even though there's a 2 there, that's the coefficient. The degree goes next to the x. Since there's no degree there, that x is 1. Same on the bottom there. Since there's no degree there, that x is 1. Since these are the same here, then I divide the coefficients. So then the coefficient on top is 2. The number in front of x, if I don't see one, would be 1. So 2 over 1 is 2. So again, that would be your horizontal asymptote of y equals 2. Okay? Same top. We're still finding horizontal asymptotes here. Now again, This one we're looking for, again, is the degree higher on the numerator or the denominator? And so in this example here, the degree in the numerator is bigger. What is the highest degree on both? On the numerator, it's 1. On the denominator, it's 2. So the denominator is bigger than the numerator. So since the degree in the numerator is less than the degree of the denominator, the horizontal asymptote has to be at y equals 0. Always going to be that way. If the denominator is bigger, it will always be y equals 0. Okay. Last one here. So in this example here, so we saw where they were equal. We saw where the denominator was bigger. Now in this example, we see where the numerator is bigger. So again, we're not looking at the coefficients. We're looking at the degree. So in letter C here, this degree is 2. On the denominator here, it's 1. So since the degree in the numerator is greater than the degree of the denominator, there are no horizontal asymptotes. Okay. So again, if the degree in the numerator is bigger, there is no horizontal. If the degree is bigger in the denominator, then the asymptote is y equals 0. And if they are the same, then you divide the coefficients and simplify. Okay. All right, this will be our last one here. And I really like this picture here to kind of help you think of this out. So when graphing a rational function here, okay, so here's our equation. All right, so your first thing you can check for is to find your asymptote. Again, you should already be able to tell the y one's going to be a lot easier. All you got to do is look at your original equation, find your degrees, right? What's the highest degree on top? What's the highest degree on bottom? They are the same. Since they're the same, then I divide my coefficients there. So in this example here, I would divide 1 over 1, which is just going to be 1, which means there is a horizontal asymptote at y equals 1. So I would draw a dotted line, a horizontal line through y equals 1. On the next part here, then we're going to find the vertical asymptote. So my first step is I have to factor that equation there. So make sure you know how to factor these out, guys. So again, when I factor it should reduce down to x plus 4, x minus 3 on top, and I can use difference of squares on the bottom there, which would be x plus 2 and x minus 2. From there, then we can look for our vertical asymptotes. Remember, those come from the denominator. So in this instance here, I would take both of those, set them equal to 0, and solve for x. So that means I'm going to have 2 vertical asymptotes here, one at -2, one at 2. So again, vertical will always be x, horizontal will always be y. Know the difference. Now from here, now we need to find our zeros here. So when the numerator equals 0, remember the numerator is the top part. So again, then all I'm going to do here is plug in 0 in for all my x's here to solve for this here. So I'm going to go back to this factored equation here, plug in 0. So again, 0 plus 4, 0 minus 3, 0 plus 2, 0 minus 2, and simplify. So that would leave me with 4 times -3 on top and 2 times -2 on the bottom. So again, 4 times -3 would give me -12. 2 times -2 would give me -4. -12 divided by -4 would give me +3, which tells me that the y-intercept will be at 0, 3. Again, that's how we find our y-intercepts. Whenever x is 0, what is the y? And at this point, it's going to be 0, 3. So again, from here, you can always get more points on the graph whenever you type this equation into your calculator and get that from the table. So again, whenever they ask you to graph these guys, just know that how you can find your horizontal, how you can find your vertical, and how you can find your y-intercept. That's really the main things you're looking for. And again, if they ask for more points, type it into your calculator, go to your table, and you can always find more points that way. Okay. But again, I really like the layout of this, so that's why I wanted to post a picture so you could see this. Okay. But guys, that's going to wrap it up for our final lesson here. Your homework will be due on Friday at 11:59 p.m. Your last chance reversal office hours will be from today. Will be from 1 p.m. to 2 p.m. Remember, Friday I can't do it. I'm going to be busy. And then if you have any questions, please feel free to contact me. I will be here for you guys. Email me, remind me, do whatever you have to do to get in touch with me if you need to. Okay. Other than that, guys, stay safe this weekend, and I will see you guys next week.